second week of Geometry Online. We are going to be leaving our quadrilaterals and our triangles for a while and talking about circles. There's lots of stuff we know about them already, but there's lots of new stuff we're going to learn. The first thing I want to mention is you are going to be answering 3 questions for me on a sheet of paper that you're going to turn in online. There are going to be 3 questions throughout. We're going to start with a joke, okay? So the first thing is, what did the triangle say to the circle? We're going to wait for the answer at the end. See if you guys already know what it is. But we'll come back to that. All right, so let's start with what we already know about our circles, and then we're going to add a few more things. First of all, we have circle P with our center point P. We're going to actually write that down here. The center is a point. This time it's point P. And we use that center point to name our circles. We would call it circle P. You'll also find now that in your book they'll use a symbol circle with the center point to name it, circle P. We also define a circle as a set of all points that are equidistant. If you remember, that means equally distant from the center. So our circle is actually a set of points, okay, that are the same distance from our center point. We've already talked earlier in the book, or this year, about a radius. The radius, if you remember, is the length or the segment from the center to any point on our circle. So PM would be a radius. Some of your homework is going to ask you to name the radius. If there's more than one, hopefully you can see we actually have 4 radii. That is our plural form. Radii. We have PM and PR. They're kind of easy to see, but hopefully you see that PA and PB are both radii as well. PA and PB. Okay, so if they ask you for a radius, any one of these would work as an answer. Okay, and then last we talked about earlier the diameter of our circle, and that is a segment that goes from one point on the circle to another point, but has to pass through the center point. Okay, so the only diameter shown here is segment AB. Okay, now we're going to add a few more segments that we've not talked about before, but I'm going to erase our 2 radii here at the bottom just to give me a little bit more room. Thanks for waiting. Okay, we're going to start by adding some new segments to our circle, and they have special names. The first one is called a chord. A chord is a segment that goes from one point on the circle to another point, but it does not have to go through the center like the diameter. So a chord might be, would look something like this. We'll call it, give it 2 points there. Point CD, segment CD is a chord. It goes from one point on the circle to another, but doesn't have to go through the center. So that means, when I say it that way, that AB is also a chord, because it does go from one point to another point on the circle. Just happens to go through the center, so it is both diameter and a chord. Okay, now a secant is a line that passes through the center, through the circle at 2 points. We'll call this one MN, use our N again. MN, line MN is a secant, but notice that it does have a chord inside it. Segment MN is a chord. So notice the chord is always a segment, and the secant is going to be a line that passes through. So line MN is a secant, but segment MN is a chord. Notice the difference there, because they're going to ask you that. All right, the last one is called a tangent line. That's a familiar word we talked about when we were doing our ratios. But this time we're talking about a line that touches our circle in only one point. So think of it as kind of this line coming up here, and as soon as it touches the circle, It's only going to pass through that one point. I know everything's kind of on top of each other, but hopefully not too bad. I'm going to make this point T here. Let's name a point out here, S. So we would say that line TS is a tangent line. It touches the circle at only one point. And we'll go ahead and put this TS, line TS is a tangent. But we could say, this one doesn't have to be a line. It could be the ray TS. Would also be tangent if it touches at that one point. Okay, now the point that it touches at, if you look down here, is called the point of tangency. So point T would be the point of tangency for that tangent line. So lots of new terms. It means you're going to be working on your notebook a little bit for you to get used to. So some of your homework, they're just going to give you a picture and say name the tangent, name the diameter, name a radius, name a chord, etc. like that. Okay. Okay, we're back. I wanted to make a note for you of something about the radius and the diameter. Sometimes when they ask the question, they are talking about a segment, which we've talked about before. You can name the segment, but sometimes they are asking you for a length. So watch how they ask the question and watch the context of the question. But sometimes when they say a radius, to name a radius of the circle, you would say, okay, AR is a radius of the circle. When they ask you for the radius, often they're saying 5 would be the radius of the circle. So watch how they ask it. Same thing, a diameter might be AC. AC is the diameter of the circle. If they ask for the diameter, again, look at the context of the question, but they may be asking for the number 10 is the diameter. Okay, just be careful of that. Okay, here's question number 2. You're going to write this down on the piece of paper, or type it up and hand it in to me. Question number 2 says, what is the line called that intersects a circle at 2 points? So write that down. Okay, let's go over a few more concepts and terms that you're going to learn. They're going to talk about coplanar circles. If you guys remember coplanar from a long time ago, those are things that happen to be in the same plane. So when we're talking about coplanar circles, we're just talking about circles on this flat surface here. Okay, so when we have coplanar circles, they may intersect in 3 ways. Of course, this one would be not an intersection, but they either will intersect in 2 points, 1 point, or no points. Now I'm going to draw the circles and be nice to me because I'm drawing with freehand. All right, so we got 2 circles may intersect, or they cross into each other, and you would say these are their points of intersection, and they intersect at 2 points there. Another way circles can intersect in 1 point would be if they are tangent to each other. We would call these tangent circles. Another way you will see that is sometimes, whoopsie, they are inside each other. I'll draw one over here. Or they share that point over here. They are tangent circles. They only touch at 1 point. And another way they may not touch, obviously, if they don't touch at all, but sometimes you'll see them inside each other, sharing that center. These are called concentric circles. I do see those. Concentric circles do not touch, they do not intersect, but they share the same center point. Okay, now we are going to focus on tangents with our circles. The first thing is we're going to look at drawing them, and sometimes they're going to ask you to draw common tangents, and that means kind of how it sounds, where the 2 circles have a tangent in common. Okay, let's see what kind of tangents we might have here. This is going to be hard to draw freehand. I'll do my best. So it's a line that touches both circles in 1 point. Pretend that one touches there. Okay, you would say that is a common tangent. And remember, tangent can be a ray, a line, a segment. It doesn't have to just be a line. So this would be a common tangent line, but notice that it might have other common tangents. going this direction as well. So we can have more than one common tangent. There's a couple more there, but I might let you find that on your homework. And then here we go. These two, they touch at one point. So really, this is one tangent that is possible because they touch at that one point. They can all have that line go through there. And again, there's a couple more there. Think about it. When they ask you to draw those, see if you can find those common tangents. Okay, let's focus on a tangent on our circle here. I drew it with my ruler, so hopefully it looks a little better than the last one. We'll call this circle C and tangent T here. Okay, so I want to draw the radius from C to T and think about what it looks like when I draw that radius. Hopefully it looks like it. With the line just touching the circle, it should look like the radius and the tangent are perpendicular. And this leads us to our first theorem. You didn't think we didn't have any, did you? Theorem 10.1. All right, back. You didn't want to watch me write all that out, I'm sure. Theorem 10.1 states, in a plane, a line is tangent to a circle if and only if, you guys remember that, if and only if, the line is perpendicular to a radius of the circle at its endpoint on the circle. So this means, remember, that it's biconditional, means that it goes both ways. So a line we can tell is tangent if we can tell is perpendicular to the radius, and vice versa. If we know that a line is perpendicular to the radius, then we know it is tangent. It goes both ways, okay? So let's look at how this might be helpful to us. Let's do an example. Okay, here's our first example. We said in the diagram below, AB is a radius of circle A. Here we go, AB. Is BC, this line, tangent to the circle, A? So if you remember, if it's a tangent by our last theorem, theorem 1, then this right here needs to be a right angle. It's going to be perpendicular to the radius. Now remember, a couple chapters ago we talked about how you tell a triangle is a right triangle, and we hopefully think back to our Pythagorean theorem. If our Pythagorean theorem is true, the two legs squared added together equals the hypotenuse squared, then we do have a right triangle. So we need to ask ourselves that question. They give us the numbers here nicely, so we do the two. This is my right angle, and these would be my two legs. So we've got 25 squared plus 60 squared, and here's our question. Does it equal 67 squared? Makes that a little better. 67 squared. So that's our question. So we're going to go ahead and work these out. We wind up with 25 squared, which is 625, plus 60 squared is 3,600. And this one's our little question mark. We need to work this one. Look this one up here. 67 squared was 4,489. When we add these together, we wind up with 4,225. Is that equal to 4,489? The answer is no, not equal. So therefore, this is not a right triangle, and BC is not a tangent. Okay, so right triangle, think Pythagorean theorem. Okay, let's do another example using our theorem. I wanted you to notice the way they worded the questions. I want to do one like this. In the diagram, S, which is point S, is a point of tangency. Find the radius R of circle T. So when they tell us that S is the point of tangency, we know automatically that this is a right triangle because the tangent line is always perpendicular to the radius at the same point. So we're going to go ahead and mark our right angle there. So that means, again, we should know that we can use the Pythagorean theorem to solve this problem. Notice the algebra gets a little interesting here because we know that the two legs squared, R squared, 48 squared, when we add them together, should equal the length of the whole hypotenuse. So we wind up having to add the two segments that we know together. This segment is the radius from here to here, but this segment is what we know is 36 centimeters. So let's see if we can do the algebra here. We got r squared, which is this leg, plus 48 squared, the other leg, must equal the hypotenuse, r plus 36 squared. All right, so don't let it scare you, but remember, r plus 36 squared, we're going to wind up foiling that. So let's work that one out. This side we'll just kind of leave alone for now. R squared, 48 squared. If you like to work out with the big numbers, you can do that first, but I'm just going to leave it like it is for now till the end. Okay? When we FOIL, remember we do the first. You could always rewrite it again, r plus 36 times r plus 36, so you can see the first outside, inside, and last. So we're going to do the first is going to be r squared. The outside we get 36r. We multiply the inside, 36r, and plus the last would give us 36 squared. Okay. Now if you look at it, we wind up with r squared here, but we have r squared on both sides. So if I subtract that out of both sides, he just goes away. So we don't have to do our factoring if it's been a while. And then we look here, let's go ahead and combine our like terms here. So we got 48 squared now equals 36 plus 36, or 72r, plus 36 squared. And we're going to get r by itself, so we're going to move everything to the other side and leave 72r there. We're going to subtract 36 squared. 48 squared minus 36 squared equals 72r. And now we're going to go ahead and put that in our calculator. I have it written down here. So 48 squared minus 36 squared, if I grab the right one, should be 1008 equals 72r. And then last we divide by 72. So r, which is our radius, is going to wind up equaling 14. Okay, so they're going to ask you a couple of these. Make sure you remember how to do the FOIL method to work out the square of the binomial. Okay, let's look at what we have here. We have a circle, circle P, and a point outside my circle. We have two tangents coming from the same point outside my same point S outside my circle. We would call this an external point. And I want you to notice something. We're going to actually derive or come up with our next theorem. Okay, since we know that these are both tangent points, we have two tangents from the point S. We know that this radius to here, this point, and I should have gotten my ruler. The radius from this point to that tangent point is going to be perpendicular, and the same thing here. Radius from the center to the other tangent point, we call them AB. We want to. Okay, we know that they are perpendicular, and if we draw a line, maybe I better get my ruler this time, and draw it from the center to my external point here. See if you can tell me what you see. Okay, let's pretend we actually hit the point. Okay, try that again. Okay, tell me what you see. We have two right triangles, hopefully you see that, and we know that the radius is congruent to the radius over there. Since it's the same circle, these two segments must be congruent, and they also share, this is my right angle, so here's my two triangles, this is the hypotenuse, and they also share the hypotenuse. So what do you know about these two triangles? Without me telling you, give you a second. Okay, and hopefully you notice they have a leg congruent and a hypotenuse congruent. If you remember from a while back, the theorem, the hypotenuse leg theorem, told us that if two right triangles have the hypotenuse congruent and legs congruent, then the two triangles are congruent. If these two triangles are congruent, then the segment SA and segment SB are congruent, and that gives us the next theorem. If we have two tangents from the same external point, then we know by this proof here that those two segments must be congruent. Okay, let me go ahead and write the theorem out for you. Okay, I've written the theorem 10.2 for us, and we're going to use it then to help us solve this problem. Theorem 10.2 says the tangent segments from a common endpoint are congruent, which we just proved. So from D here, we're told AD is a tangent to C. So we have AD from this common endpoint with BD, and BD is tangent to C also. So from our theorem, we know that the two segments, AD and BD, are congruent, which means that their lengths are equal, and we're going to set them equal, and we can solve for x. 25 equals 6x minus 8. We're going to add 8 to both sides. So 33 equals 6x. And to solve for x, we get divide by 6. So our x then, when we divide that, we wind up with 5 and 3/6, or 1/2. 5.5 is our answer. Okay, here's question number 3. Again, write this down and turn in at the end. If RS, segment RS, is tangent to circle C at point S, and segment RT is tangent to circle C at point T, what do you know about RS and RT? Give me an answer. Okay, that concludes our section 1 on circles. We have lots of terms for you to get in your head, being able to find secants and chords. Also, we learned lots about the tangent lines, that they're perpendicular to the radius where they touch, and also that two tangents from the same point, external point, are congruent, so we're using those. But also, did you figure out our joke, the answer to our joke, which was, if you remember, what did the triangle say to the circle? You're pointless. Alright, don't forget to write that down, answer the other 2 questions, and good luck on your homework, and we'll talk tomorrow. See you.